Good day, everyone. So today we're going to be talking about the Fermi golden rule, and it's a continuation of our discussion on the time-dependent perturbation theory, but is used to calculate rates of transitions into a continuum. And these would include examples such as ionization of atoms, beta decay of nuclei. They're a couple of famous examples. Photoelectric effect is another. So the example that we're going to talk about is ionization of a hydrogen atom. So for example, we have done previously, if we look at the energy spectrum of hydrogen, we know that it looks something like this. N equals 1, N equals 2, and so on, up to N equals infinity. And if I said to you, and this is, of course, in energy space, and that's 0 at this point. So that's the axis at the top there. And above that, you've got the continuum. So then if we said, okay, let's have a photon coming in, tuned close to something like this transition frequency, and we had some electric field, E naught cos omega t, which is approximately equal to omega 1, 2 here, then we know how to treat this system. It's a discrete to discrete system, and we know we get the Rabi oscillations. So we've done that last time, and we're going to use those results. But now we're asking a slightly different question. Instead of this, we've got the same setup, but we want to know what happens if we have an electron being kicked out from here all the way up into the continuum, some level up there. And so this second system will have h bar omega greater than the binding energy of hydrogen. And it will push the electron all the way out of the atom. And now we want to know what is the rate at which it can push the electron out of the atom. How often does this happen? So first thing we're going to need to do is define the density of states and remind ourselves of what density of states is. Because when we're talking about the wave functions in the continuum, what are we talking about? Now, if we forget about the fact that we have an atom at all, just for a moment, then what we're going to have to do to define the density of states is we're going to have to discretize our space. So we invent a box like so, of length L, and the wave function that we know is that of a plane wave. So we have a set of solutions which are plane waves, and they'll have wave vector k, and it's a very big box, right? This is a box the size of the laboratory or something like that, or perhaps it's the size of the universe just as well. And but we've discretized it. It has edges, L cubed, and we can use cyclic boundary conditions, periodic boundary conditions. We can just put a hard wall there. It doesn't really matter too much. And let me just write this out, expanding the dot product. Kxx, Kyy, Kzz. What's the L cubed doing when we integrate psi squared for the plane wave? We then will have it normalized when we integrate over the entire box. So that's where the 1 over square root L cubed comes from. The boundary conditions, which we'll take as periodic, will give us Kxl equals 2 pi nx, and same for ny and z and nz and so on. And so dkx is equal to 2 pi over L dnx. And now we want to count up all of the possible states. So to do that, we count the states by integrating dn is equal to dnx, dny, dnz equals L over 2 pi cubed d cubed k. And that is the density of states around some little area interval of k. So remember what we're doing here in k space. So this is kx, ky, and kz. In this space, it's discretized. So we have some kind of a grid in here. Hard to draw in 3 dimensions, but you get the picture. And then we have some particular vector k, and that will make a little space that we can, that's supposed to be a box, like that. And that's my d3k, and I want to know how many of these dots are inside that box. And that will be the density of states for a particular energy. So how does that work? So first thing we need to do is expand out the k. Before we get to that, I'm just going to write that the energy of every state with wave vector k is h bar squared k squared over 2m, which obviously doesn't depend on the direction of k, it just depends on its magnitude. And so I can write dE k is equal to h bar squared over m times k dk. And using that, I will then have dN is equal to L over 2 pi cubed times d3k, which is k squared dk d omega, so that's the solid angle. And then I can write that as L over 2 pi cubed. And now I will take one of those k's and I will keep it, kd omega, and the other k dk I'm going to replace with m over h bar squared dE. And so this part here is the density of states for a particular value of k. Okay, so hopefully that's not something that this is the first time you've seen, otherwise I've done a terrible job of it. We want to use this in our calculation to find the rate of ionization. So we're going from the bound state to a continuum state. So last time, for discrete to discrete transitions, we wrote the expression for the probability of going from state A to the state B as a function of time. And that ended up being something like sine squared omega t. So let's just remind ourselves of that. It looks something like and so on. And this is for discrete, and it starts off with a kind of a quadratic down here, because that's what sine x does. So this is sort of quadratic in time down here. And if you wait longer, then it stops being quadratic and starts being sinusoidal. So that's what we expected from the discrete to discrete transitions. It'll be different for discrete to continuum. So what we want now is to know the rate of the transitions to final states in the continuum. And the point here is that we have many states. It's a continuum. So for a given oscillatory electric field, we would have many different possible final levels because they're all extremely close together. So what we actually want is to sum over all the possible final states as a function of time and get that probability. Of course, there's many of them. Many of the final states, they are in the continuum. They're infinitely close together. And so how do we deal with that? Well, we turn that into an integral. Now it's I goes to F times the density of states DEF. And we're integrating over some little region of final states. So you can think of that, for example, as my laser has a finite width. It's not just purely monochromatic. It has some finite width, and that finite width leads to a range of final states, but all around the known final energy. And so what is that final energy? EF is approximately equal to the h bar omega of the laser minus the binding energy, the magnitude of it. So that's where they're going to be, but they're going to be in some finite little range, delta EF, which depends on, for example, if it's a laser, what's the width of the frequencies? Or alternatively, if it was perfectly monochromatic, I would run my experiment for a certain length of time, and then that length of time leads to a finite resolution via Heisenberg's uncertainty principle, or equivalently just by doing a Fourier transform over a finite time. And so then you end up getting a width anyway. So this is what we're looking for. And what we can do now, I'm going to give this a name. I'm going to call this the probability of ionization as a function of time. Okay, probability of ionization as a function of time. Cool. So Pi of t is equal to, now we've already solved this before, so let's just put in our solution. We've got an integral delta EF. The solution to Pi to F was U Fi squared over h bar squared, and then we had a sine squared omega naught minus omega t over 2 over omega naught minus omega squared. So that was our probability of transition in the discrete case. And now we need to integrate that over the density of states, DEF. And what is omega in this equation? Omega naught was EF minus EI over h bar. And we also, we need to remember what UFI was. We had VFI was equal to UFI over 2 cos omega t, or e to the I omega t. Now the thing is, we can take our initial state here, I, we're hitting it with some photon. It's at some binding energy here, so there's 0. And this is the binding energy, EI, and we're hitting it with some photon that takes it up to here. It should be in energy space, so this is h bar omega, and the final energy here is EF. Right, so this is 0. So all of this up here is continuum. So now what we can do is we can look at the density of states around the little bit of EF that we're going to have. So that is essentially constant. Similarly, UFI is going to be essentially constant. So we can write actually PI of T. We can take out these constant values. UFI is constant, approximately constant in the narrow range of EF around where the final electron is going to go. And similarly, the density of states doesn't change too much. And so now we're left with this integral, little range delta EF, sine squared and in that integral, the EF is hidden inside the omega naught. We can solve this integral. It's kind of a little bit of a tricky one. So let's just make some manipulations. We're going to make this substitution. U is equal to omega naught minus omega times T over 2. And that, I remind you, is T over 2, because that's omega naught is where our EF is. So that's EF minus EI over H bar minus omega, like this. And so we can say du is equal to T over 2H bar times DEF. And that means that we can write this integral as the integral over a little section delta U, which we'll come back to in a second, sine squared U over U squared. And to get that U squared, I need to multiply the omega minus omega naught by 2 over T. So I'll write here 2 over T squared. And then I need to put in DEF needs to become du, so that'll be 2H bar over T du, which is, now I'll take the H bar and the T's and the constant factors outside, and I get du squared, and this is sinc squared function, which we know well from single slit diffraction. We've seen this before. So how do I integrate this sinc function, and what is the range delta U? So firstly, let's talk about the sinc function. It looks like this. Sine squared U over U squared versus U, something like this, where those tails are very much exaggerated. And what we're doing is we're integrating this function and what's the range? If I integrate this function between minus pi and pi, I get 90% of its total value. If I also include the second little bumps up to 2 pi, then I get 95%. Let's think about the range of U that is appropriate for us. The large time period that we're going to take, so if t is large, then U is also large. And what we're thinking about here is that we're going to run the laser for long enough that the U is very large. And that means that the delta U is large, or another way of saying it is that we're making the delta omega actually quite small. So this distance here in between this first harmonic is going to get narrower and narrower and narrower as we run t for longer. So if t is large enough, this thing is going to get smaller and smaller and smaller. And so if this is small, then we can do this whole integral and we get 95% of it, or we can just do minus infinity to infinity, knowing that it converges for t large enough. The trick here is that we need to have t large enough to make this integral work, but not too large, so that p of t is still treatable by perturbation theory. And in fact, we can do that. And so for typical examples, we'll have the time which is going to be running for long enough so that perturbation is still work because the perturbation is small, but t is long enough that we can do this integral sine squared u over u squared, assuming that you're going from minus infinity to infinity. And then you can do this exactly, and it's pi. And pi of t is now ufi squared over h bar squared, density of states, h bar t over 2, and the integral is now pi. So it looks very, very simple. Usually one doesn't see it in this form. Usually one sees Fermi's golden rule in a different form. We actually write the rate W for our ionization process is dp dt. It's the probability of transition per unit time. And so this divides out the time that's in the numerator. And so one gets a time-independent rate. The last thing we need to do is put the u in terms of the peak v. So we'll write this as 2 pi v fi squared. One of the h bars cancels out. Density of states of the final states. And often you'll also see it with a little delta function which is to guarantee that we have conserved energy. And in this form, it's actually quite robust. You can use it for many, many different kinds of problems. So this is Fermi's golden rule. Now, I want to go back just quickly to our example of hydrogen. I'm not going to solve it completely because it's a little bit involved, but one takes the initial wave function as, say, the 1s wave function of hydrogen. The final state is one of those plane waves. There's a little bit of trickery going on here because I have a final state which doesn't include the atom itself. This, when I was looking at this plane wave, I assumed that it's not perturbed by the atomic potential, by the proton at all, and that's true providing that the energy of the ionizing photon is large enough to drive it very far to quite high energy. So in other words, this EF should be much larger than EI, unlike how it's drawn here, in order to have a plane wave solution. And if you do this, then you see that you're going to have the VFI is going to be proportional to 1 over the square root of L cubed. And so VFI squared rho of EF is going to be 1 over L cubed times L cubed, which is order 1. So dependence on the size of the box disappears. And that's also quite typical. It should happen. In other words, it shouldn't matter whether I'm doing this experiment in a lab or in open space, I should get the same answer. And so that depends on L cubed, which is coming from VFI, but also coming from the density of states. They'll exactly cancel each other out. So I think this is a good place to stop talking about Fermi's golden rule. We don't deal with we don't want to go too deeply into continuum states here. And so let's just leave it there. It's a very general formula, but it can be a little bit more complicated to apply. I'll see you next time.